Lesson 73 has two parts. The first part is on factoring the difference of two squares, and the second part we'll be learning some more about probability. So the first part of this lesson is on factoring the difference of two squares, or basically two terms or two polynomials that are squared polynomials. A squared polynomial might be something like this, 4a squared, which you could take the square root of, and that would just equal 2a. So a squared polynomial is one that we could take the square root of and just get a square root answer for it. Because like for this one, we could just multiply that again by 2a to get back to what's inside the radical sign, 4a squared. Now think about this title, factoring the difference of two squares. So difference, that means subtraction, right? So if we had 4a squared minus another squared polynomial like x squared, you can actually factor that into two binomials. And what you do is just go ahead and set up a pair of parentheses, and you think about the square root of each of those terms. Like the square root of 4a squared would be 2a, and we put that at the beginning of both of the binomials. And then that minus x squared, well, the square root of x squared would just be x, right? Because x times x equals x squared. One of these we put a positive x, the other we put a negative x. That's how we factor the difference of two squares. Now we can always check our work and make sure that we really did that correctly. Let's take the 2a on the left, multiply it by the 2a on the right. That would give us 4a squared. Then multiply it by the negative x. That would give us negative 2ax. Then take the x on the left, multiply it by the 2a on the right. That would give us a positive 2ax. And then multiply it by the negative x, which would give us negative x squared. So do you see those two terms in the middle? They are like terms, but the coefficients are opposites of each other. So those would cancel, and we would get back to that original expression, 4a squared minus x squared, the difference of two squares. So the key to doing these problems is really just recognizing that you have the difference of two squares. And so try to remember what I have on the board there. Use that to think about how to set the problem up. Recognize that you have the difference of two squares. Well, how do you recognize that you have the difference of two squares? Well, it's pretty easy. You have two terms. There's a subtraction symbol in between them because it's the difference. And both of them are squared polynomials. So in the problem sets, they'll ask you to factor these binomials, and you'll think, well, all I've done so far is factor trinomials. Try not to skip back to that. Say, oh, well, I've got two squares here. I've got a difference of two squares. So there's a lot of things that will give you a hint that you're factoring the difference of two squares. The minus sign in between them, the fact that there's only two polynomials there in that expression, and also that they are both squared terms. Let's do practice problem A. Let's factor that into two binomials. So basically we're factoring a binomial into two binomials. That seems kind of strange, but that's what we do here because we recognize we have a difference of two squares. We see the subtraction sign, and then we see that 9x squared, well, that could be 3x times 3x, so that's a squared term. 25y squared, that's the same thing as 5y times 5y, so that's also a squared term. So we put some parentheses down. The first term in that squared binomial, that always goes first in the two binomials that you make. 9x, or not 9x, I'm sorry, 3x. We always take the square root of that binomial, so that'd be 3x and 3x, and then plus 5y and minus 5y. And always, especially right now, you should go ahead and check your work to make sure you did them right, and you do that by expanding that back out. So let's just go ahead and do that on this one. 3x times 3x is 9x squared. and then 3x times a negative 5y is minus 15xy. Then the 5y times the 3x is positive 15xy. And the 5y times the negative 5y is minus 25y squared. And so do you see how those middle terms, they always cancel like that? And so we get 9x squared minus 25y squared, our original expression. So this is the factored form of that difference of two squares. Look at practice problem B. Now this one, we want to factor it just like the last one, but it doesn't look like a difference of two squares. The polynomials, the individual polynomials, do look like squared polynomials, right? 36x squared is the same thing as 6x times 6x, and then y squared is y times y. So we're dealing with squared polynomials. However, we've got a negative up front. Well, all you have to do is just rearrange this and make it y squared minus 36x squared. So that's all you have to do. Now it looks like a difference of two squares problem. And so let's go ahead and factor it out. So we put a y here and a y here. And then we could put a plus 6x or a minus 6x. It doesn't matter if we put the plus or the minus first. It's just that we have to have opposite terms there. And so that's our squared binomial factored out. Let's do one more. X to the fourth, y to the fourth, minus 144, a to the sixth. Well, we see two binomials there. We see a subtraction symbol in between them. Now, it may be a little more confusing to recognize the difference of two squares there. Well, just think about it for a second. X to the fourth, y to the fourth. Wouldn't that be the same thing as x squared, y squared times x squared, y squared? Well, it would. And then 144a to the sixth is the same thing as 12a cubed times 12a cubed. And so we do have a difference of two squares here. So let's go ahead and set up some parentheses. And first in each one will be x squared, y squared. And then in this first one we'll say plus 12a to the third. And then in the next one minus 12a to the third. Okay, so there's our factored form of that squared binomial. The key to doing these problems and to factoring them out is recognizing that you have a difference of two squares and then recognizing what the squares are for each of those. Let's go ahead and do one more. Minus a to the fourth plus 81x to the 10th. Now, just like the factoring trinomial problems, these have to be able to factor into two binomials. So when you see binomials like this that are real big, have lots of high power exponents, you can almost just assume that you're going to be working with a difference of two squares problem. So you just kind of know that it's going to factor into two binomials. This one, we just need to rearrange it to make it look like the difference of two squares. So now it looks like the difference of two squares. Now let's go ahead and factor it. And at the beginning of each binomial, we'll have 9x to the fifth. And then we can have plus a squared minus a squared. So that's our factored form of that squared binomial. 73b is on probability without replacement. Now in lesson 70 we learned about what probability is, and I've written an abbreviated form of that relationship there. It's a quantitative evaluation of a chance of something happening, and it deals with the number of desired outcomes divided by the total number of possible outcomes. Now let's apply what we know about probability to a special type of problem. This deals with replacement and not replacing certain values. So look at practice problem E. It says that an urn, which is like a jar or a vase, it contains 6 orange marbles and 6 maroon marbles. Two marbles are drawn at random. What is the probability that both are maroon? 1, if the marbles are replaced after observation. So after you look at them, you pick one out, look at it, put it back, pick the other one out, look at it, put it back. Or 2, if the marbles are not replaced after observation. So let's think about what we're dealing with here. We're picking two marbles out at random. So that means when you hear that word at random, they're talking about independent events. So you multiply the probability of each event occurring together. So the first event is 6 over 12, right? The probability of picking a maroon one on the first try, because there's 6 maroon ones, there's a total of 12 marbles. So the probability is 6 over 12. And then on the second try, the marble, that first one was replaced, so you still have 6 maroon ones in there. The probability of getting a maroon on the second try is again 6 over 12. So we just say 6 over 12 times 6 over 12. Hopefully you can just do this in your head. That'd just be like saying 1/2 times 1/2 equals 1/4. So there's a probability of basically 25%, or 1 in 4, that if you picked up a marble, then replaced it, picked another one up, both times you would get a maroon marble. Now number 2, what would happen if the marbles were not replaced? What would the probability be then? Well, just think about it. You go in and you pick a maroon marble. The probability of getting a maroon marble on that first try is 6 over 12. Okay? But now you have taken one of those marbles out. You did not replace it. So now you only have 5 marbles left, and so the probability of picking a maroon one again is 5 desired outcomes over not 12, but 11 total. Now it has to be 11 total because you only have 5 maroon, 6 orange. That totals up to 11. So that's why it's 5/11ths instead of 5 over 12. 6 over 12, that can just be simplified to 1/2. So the answer here would be 5 over 22. So there's a 5 in 22 chance, basically, of getting a maroon marble twice when there is not replacement, when they're not replaced. So something to think about here. Without replacement, your probability of getting a maroon marble twice, that goes down. But your probability of getting an orange one on the second try, that goes up. So the important thing to remember on these problems where you don't have replacement is that you need to change your desired outcomes as well as your possible outcomes. Make sure you change both of those when you have a problem where there is not replacement, where you take something away and don't put it back in, and you need to calculate the probability for another event after you've taken something out. Okay, well that's all for lesson 73.